Hello, this is lecture number 3 for the mini course on Einstein manifolds with symmetry, or the third geometric analysis festival. So the aim of this third lecture is to explain the proof of the Alekseesvskii conjecture, which states that any connected homogeneous Einstein space of negative Einstein constant is diffeomorphic to a Euclidean space. So as I mentioned in lecture number 1, we will sketch the proof in the particular case where the manifold is the Lie group SL2C of dimension 6. Remember, this is diffeomorphic to S3 cross R3, so it should not admit any left-invariant Einstein matrix. And this is what we will show. And the main idea is to apply, again, well, the goal that I just mentioned. And to show this, we will apply Theorem B. So let's assume to begin with that G is a left-invariant Einstein metric on SL2C, right? And let's try to reach a contradiction. So how does one apply Theorem B? I mean, a priori, it sounds like complicated, right? Because we have a semi-simple Lie group with a left-invariant metric, and then Theorem B has as an assumption that the near radical of our Lie group is non-trivial, but the near radical of semi-simple Lie group is trivial. So the way one applies Theorem B, and this is why it is so strong, is that we take a subgroup of SL2C, which is solvable, and whose corresponding quotient is compact. And the way to do that, to consider such a subgroup, is to look at the Iwasawa decomposition. So let me recall what the Iwasawa decomposition is. So this is not important, but it's an assumption that I'll be using in a minute, so that's why I mentioned. Any non-compact semi-simple Lie group F decomposes as a product of subgroups K times A times N. This is the product inside of F, right? But this is actually diffeomorphic to the product of these smooth manifolds, K times A times N. So here, K is a maximal compact subgroup, so that in particular, F mod K is a symmetric space, and G, defined by A times N, is a solvable Lie subgroup, and moreover, they don't intersect. Okay. For example, if F is SLNR, then K is just SON. You can take A as the diagonal matrices in SLNR with positive entries, and you can take N to be the subgroup of SLNR of upper triangular matrices with ones on the diagonal. And some people refer to the Iwasawa decomposition in this setting as just being a consequence of the Gram-Schmidt's orthogonalization process. For our case, where F is SL2C, this gives a decomposition of SL2C as a product of SU2, which is its maximal compact subgroup, times a three-dimensional solvable Lie group, which is in fact isomorphic as a Lie group to the hyperbolic group that we were working with in lecture number 2 for the case of dimension 3. Right? So this group acts transitively on hyperbolic three-dimensional space. Well, because G is a subgroup of SL2C, and the metric G is invariant on the left multiplication by SL2C, it's also invariant on the left multiplication by G. So in particular, this G acts freely and isometrically on our space. And the orbit space is, of course, diffeomorphic to SU2. So it's a compact, smooth manifold. Therefore, we may apply Theorem B to this G action and conclude that all the rigidity conditions that we mentioned hold. In particular, the N submersion has integrable horizontal distribution. And another condition which I did not mention, but which also holds and will be important, is that the mean curvature vector of the n orbits n induces on P a parallel vector field, namely nabla n restricted to horizontal directions is identically 0. So this is given by Theorem B. Right? So now, before we continue, unfortunately, we have to refine the conclusion of Theorem B in this particular case, because otherwise it won't be enough for us to reach a contradiction. And the refinement in this setting goes as follows. So under the assumptions that I mentioned above, one can in fact show that this foliation by minimal Einstein submanifolds is in fact the same as the foliation given by the G action. So in other words, the G orbits with their induced submanifold geometry are Einstein themselves and minimal. Okay. So let me give an idea of how to prove this theorem. This in the paper is actually the content of section 11. So it looks slightly different. That's why I mentioned the correspondence. But in this setting, this is what we have to prove. And so what's the idea? The idea is the following. So remember that the n orbits are of codimension 1 hypersurfaces inside, the G orbits in M, right? Simply because n is of codimension 1 in N. Recall that in this case, N is just an abelian two-dimensional Lie group. So let us take n tilde to be the mean curvature vector of these n orbits inside the G orbits, okay? So as submanifolds of a G orbit, there will be a mean curvature vector, n tilde, right? And then there is also the mean curvature vector of the n orbits as submanifolds of M, right? Which might be different in general, of course, because the G orbits are not totally geodesic in M. So to prove Theorem B plus, we have to show that they are actually the same. So the good thing about n tilde is that it's an n-invariant vector field, and therefore it induces a vector field on P, which is a quotient of m by n, and this is in fact a killing vector field on P. This is not hard to prove. Well, but recall that n induces, so n tilde is killing on P, n is parallel on P, so in particular also killing, right? So the idea is to consider the difference of n and n tilde and apply a Bochner type argument. Right? So using the horizontal Einstein equation, together with the rigidity we already obtained by applying Theorem B, in particular the fact that n is parallel on P, we obtain the following formula for the norm of the difference between n and n tilde. So this is the Einstein equation. And then here I get the Ricci curvature of P evaluated at this term, but because n is parallel on P, this is the same as the Ricci curvature of n tilde. Now applying Bochner formula, because n tilde is a killing field, we know that the Laplacian of this function, which is half the norm of n tilde squared, is the norm of nabla n tilde squared minus the Ricci curvature. Right? This is Bochner formula. You can find it, for instance, in the book Peterson, Riemannian geometry. And by the previous formula, this curvature term can be written as a positive term plus the difference of n and n tilde. And so this has a sign. But since this function is G invariant and the quotient is compact, it follows that by the maximum principle or the divergence theorem on B, we must have equality everywhere. And that implies in particular that n equals n tilde, right? So the G orbits are Einstein. That's a cute argument. And now let us see how we use that argument now, how we use that fact. Now remember that I mentioned at the beginning, the idea for proving the Alekseesvskii conjecture is forget about homogeneity and focus on these non-transitive actions, right? So this is what we did, and then we proved theorem B, and then we applied it in our situation. But now, well, we kind of have to remember that our space was homogeneous, right? Because it's too much information to throw away. So it was good to forget for a couple of months, but now we have to remember that it's homogeneous. And why? Well, because using homogeneity together with the properties that we deduced from applying theorem B, namely that the n submersion has integral horizontal distribution and that the G orbits are Einstein, one can prove an algebraic formula for the Ricci curvature of SL2C. Just by algebraic, I mean you compute the Ricci curvature on Killing fields, right? And this is using homogeneity. And you use a basis consisting of Killing fields. And this is the formula that we use, right? So under the above assumptions, let's take P to be the identity at SL2C. And choose any basis of Killing fields EI, which is a union of Killing fields on N. So these span the vertical spaces, and a union of Killing fields which at the point P are horizontal, right? So these are always vertical. These Killing fields here, YK, they are only horizontal at P. So if I move to a different point, they might fail to be horizontal. Then UR, I said already, they belong to N, which is the algebra of N. And remember, the submersion we are considering is the one given by the N action. Now the formula we obtain is the following. It relates the scalar curvature of the orbits with the partial trace of the Ricci curvature of the ambient Ricci curvature, right? And the difference gives us this expression here where n is the mean curvature vector, and well, this is the Lie bracket of Killing fields or of vector fields of the manifold. Now the good thing is that these two terms are computable in algebraic terms. So what do I mean by that? The right-hand side one can compute. Well, first of all, by using a little bit of Lie theory, one can choose this basis EI with the property that these endomorphisms at U are nilpotent endomorphisms when written in this, nilpotent matrices when written in this basis. So this is standard in Lie theory. And now let's take a Killing field, which at the point P gives the same value as the mean curvature vector. Remember, the mean curvature vector is in general not a Killing field. It's G invariant, in fact, so it's like the opposite of being a Killing field. But in this case, at one point, by homogeneity, there will always be a Killing field pointing in the direction of this vector. And then using the Einstein condition, I mean, first of all, scalar curvature is 0 because the orbits are flat because n is abelian, as in the lecture number 2. Now the Einstein condition tells us that this is -1, and there's two terms like that, so we obtain a 2. And on the right-hand side, by the nilpotent observation, this term also vanishes. And so we are only left with this sum here. And this sum turns out to be a trace, because when you have an expression like this, where all three vector fields are killing fields, then one can look at the book of Besse, where there is a formula, I think it's 7.27, for computing the Levi-Civita connection on vector fields, on killing fields, sorry. And this gives an expression in terms of the Lie bracket, but this is nothing, because EI is a basis of SL2C, this is nothing but minus a trace of add of this vector, the adjoint endomorphism. And because SL2C is a unimodular Lie algebra, this is 0. So we get a contradiction, right? Because we get something positive on the left-hand side. And this essentially concludes the proof, indicates that M is SL2C. Now let me mention that, well, we made a number of simplifications in this proof, right? Because, well, SL2C is a special case, but what about the general case? So the main differences are as follows. Problem number one is that the group N is not abelian in general. And that's perhaps I would say, the main difficulty, because one has to take into account the geometry of the N orbits. And before this paper, I think this couldn't be dealt with, but the way we deal with this problem is, instead of considering the F that I mentioned for proving, Theorem B. Now this is a remark regarding the proof of Theorem B, I should say. We add a term to this function V, which we call the log beta volume of the N orbits. So this is like a volume which is not quite the volume, because it takes into account some Lie theoretic properties of the group N, which in fact come from a deep connection with geometric invariant theory. And this was one of the main ingredients in the construction of Lyapunov functions for immortal homogeneous Ricci flows that we did a few years ago with Christoph. And so the good thing is we were able to extend these notions to the case of non-transitive group actions. So we just apply the construction on each orbit, and it turns out that this is the right quantity to add in order to get a nice differential inequality in the case that the orbits are not flat. Now, another issue is that the group F might be non-semisimple, right? So then what one has to do is to consider a nice Levy decomposition. So any Lie group is a product of a semisimple Lie group and a normal solvable Lie subgroup, right? So the semisimple part I call L, and the solvable one I call S. Now, by the structured results for Einstein homogeneous metrics, we know that we can take such nice decomposition so that the orbits of these two subgroups are orthogonal at the identity, right? So there's a compatibility between the geometry and the Lie theory, so to speak, and this will be very important in the proof. And now, what's the group G, right? We need a solvable group with compact orbit space. So, well, consider the Iwasawa decomposition for the semi-simple part, K, Al, and L, and then simply take G as this subgroup, An times S. Then we also have to make sure that the quotient, is compact. But it turns out that after passing to a discrete quotient of the original manifold, one can always assume that's the case. That this is related to the assumption that the Lie group is linear semisimple or is general like semisimple. But I won't make any more comments because this is highly technical into the Lie theoretical side. And then an important ingredient in proving the general version of Theorem B plus, which we actually didn't see in the proof of Theorem B plus that I presented because this was automatic in our case, because this is like a very simple situation, is the fact that we have to prove that the G orbits admit G-invariant Einstein matrix. Okay, and this is not automatic, right? Because the group G is not a direct product of. So first of all, notice that this solvable group acts transitively on the symmetric space. Sorry, not L, not F, but acts transitively on the symmetric space L mod K. Right? So therefore, it has a left invariant Einstein metric for this group, right? The symmetric metric. So the same happens with S by the structures theory for homogeneous Einstein spaces. So we knew this already. Now, the problem is that G is not a direct product of these two groups, but it's a semi-direct product. And there's no theorem telling you that a semi-direct product of two Einstein solved manifolds will be an Einstein solved manifold. And I think this is false in general, right? The only reason it's true in this particular case is that the Einstein metric here comes from a much nicer, symmetry situation. Namely, it is the symmetric metric on this symmetric space, right? So it's L invariant, and so that's what makes this work, right? One has to prove this, and it's technical, but well, luckily it's still true, and it's very important for proving Theorem B plus. And then finally, the last algebraic problem that one might run into is, so it might sound weird that in the last step we get a contradiction, which is by so much, to put it in some way. So we get 2 equal to 0, right? So that seems wrong because it seems like there's no chance of getting equality, right? And in general, this should not be the case because, well, there are examples of homogeneous Einstein metrics, say the symmetric spaces, for instance, right? Now, the key point is that if the group is semi-simple, the only possibility is that you are dividing out by the maximal compact subgroup. Because in our argument, we were assuming that the isotropy was trivial, then the estimate shows that we are far away from being Einstein, because 2 equals 0, far away from being true. Now, in general, when H is allowed to be non-trivial, then the estimate in the previous slide are much more subtle, and actually, in some cases, equality holds, right? Because when H is K, equality must hold. But equality holds even in more cases, in fact. So the good thing is that when equality holds, you can conclude that there is a group which is of the form something compact times something solvable, which acts transitively on your homogeneous space. And then by the work of Jablonski and Peterson, one can conclude that, well, under this situation, then also the solvable part acts transitively. And therefore, you end up proving that your Einstein homogeneous manifold is actually a solved manifold, as we wanted to show. But again, this involves paying attention like very, very closely to this algebraic estimate and using a bit of non-trivial Lie theory on the semi-simple Lie group L. So all the details are, of course, in the paper, which will appear on the archive this coming Monday. And this is then the end of my talk and the end of the series of lectures. I hope you enjoyed. I hope you can take at least some ideas home. Hopefully there are plenty of questions. I'm happy to address. These are the references that I cited. So it's a very long list, but you will have access to these slides, I guess. So no need for having them here. And well, yeah, I thank you all for attending this talk. And thanks again to Hochu Lee for the invitation. I hope you guys have a nice day. Bye.